Chaos is a very intriguing phenomena, and the chaotic pendulum in the drop tower is very interesting because by looking at the experimental video, it is very clear that the drop tower kills chaos. And here's why. If we look at our double pendulum, which happens to be a compound pendulum, there are two axles, the primary axle and the secondary axle at the end of the first arm. The first arm is of length L1 and can be described by angle theta 1, and it has mass M1. The second arm has length L2 and has mass M2 and can be described by an angle theta 2. Now when we look at this double pendulum in the red diagram, we'll see that the center of mass of each of those two arms are located at x1 and y1, x2 and y2, and along with theta 1 and theta 2 produce 6 variables to describe the motion of the chaotic pendulum. Here in the red diagram, also the length of both arms are equal to L, and the mass of both pendulums are M equal. Now when we set the double pendulum into motion, you'll see that it does begin to behave chaotically. You can never predict what those gray lines are going to be doing. However, when you look at the actual experimental double pendulum on the left, you'll see that in the beginning it is swinging back and forth in a chaotic fashion, but once it's dropped into 0G, chaos ends, and it swings around and around the primary axle with a constant angular velocity omega 1 and omega 2 for both of the branches of the pendulums. Here's why. When we express the Lagrangian for this chaotic behavior, you can see that there's two terms in the Lagrangian, one kinetic energy and one potential energy, and the kinetic energy is expressed as translational kinetic energy and rotational kinetic energy for both pendulums, and the gravitational potential energy for each pendulum. This is the term that leads to chaos. If we include the description of the positions, theta 1 and theta 2, x1 and x2, you can see the generalized equation which leads to the two coupled differential equations which result in chaotic behavior. However, upon drop, G goes to 0, and that eliminates the gravitational potential energy term in the Lagrangian, and it eliminates this term in the equations of motion, and the resulting equations only contain the conservation of energy, kinetic energy. As you can see from the red pendulum, that as it swings back and forth, energy is conserved in the chaotic pendulum, but angular momentum is not. That is because of the gravitational potential energy term and the terms that contain G in the equations of motion. However, when G goes to 0, angular momentum is once again restored and is conserved, and energy continues to be conserved, so both pendulums rotate about the primary axis with their own particular angular velocities, conserving energy and angular momentum after drop. That is the beauty of the chaotic pendulum in the drop tower. Here at PCC, we have a challenge to all teachers in all classes to bring in world problems into our classroom for our students. The chaotic pendulum gives you a great opportunity to discuss climate change in your classroom. As you can see from the red pendulum swinging back and forth, the gray lines inside of the envelope of its motion are equivalent to weather. You cannot predict what's going to happen on a short-term basis. However, over the long term, those gray lines paint a picture of an envelope that relates directly to the energy content of the system. As energy is added, the envelope grows. As energy is removed, the envelope decreases. That is climate. And as we've seen, with energy and greenhouse gases causing energy to increase in the system, we've had more dramatic extreme behavior in the chaotic weather patterns. This is why the chaotic pendulum is such a beautiful tool for use in your classroom.